Hi everyone, this is example 4 in module 2D on page 61 of your activity packet. So the mean of a density curve is represented by this Greek letter mu right here. It looks like a cursive M sometimes. And a way to think of the mean is as the point where the curve would balance if it were made of solid material. So you can imagine if you were balancing it on a stick or something, right, that would be the balancing point. The median of the density curve is that point where you've got equal areas, so it divides the curve exactly in half. So at the median, you've got 50% below and 50% above. So this figure here in part A shows 3 density curves. And for each one of these, curve 1, curve 2, curve 3, we want to explain what we know about the mean and the median. And it's a little bit hard to see in your photocopy, so maybe you can see it better here. I'll give a description. So we'll say in curve 1, the tail is to the right, and we know that means the mean is greater than the median. In curve 2, the shape is symmetric. And in that case, there is no tail, so the mean is equal to the median. In curve 3, the tail is to the left, and we know that that means the mean is less than. So this will be in thinking about a symmetric graph, we know the mean is equal to the median. And in thinking about a left tail graph, we know that the mean is less than the median. And you can remember my hint, the mean is the same direction as the tail. So question B asks, what shape is the density curve where the mean and the median are the same value? So we see that a symmetric curve is that shape. So we can say in a symmetric curve, the mean and the median are equal. And the reason is because in a symmetric curve, there are no extreme high or low values pulling the mean. And then you could make a sketch of a symmetric curve. It would look like this curve 2 right here. A nice symmetric bell shape. Question C asks, which shape is the density curve where the mean is greater than the median? So we know in the right tail graph, the mean is greater than the median. And then you can sketch what a right tail graph would look like. It would look like that first graph, curve 1. Okay, let's look at example 5 on page 62. So in example 5, we introduced a standard deviation. And what standard deviation does is measure how far away our data is from the mean. So here we have 2 curves. It's hard to see them in your packet that they're different colors because your packet's only black and white. So I'm going to go ahead and label the bottom curve as the red curve and the upper curve as the blue curve. So we want to describe the differences or similarities in the shape, center, and spread of the distributions. So both graphs are symmetric. They're also both centered in the same spot at 50. However, we see that the red curve has a wider spread. Notice the red curve goes all the way from 10 to 80 or 90, I think to 90, whereas the blue curve only seems to go from 30 to 70. So we can say the red curve has a wider spread than the blue curve. So then, remember, standard deviation measures how far the data is from the mean. So which of these graphs is going to have a larger standard deviation? Well, the red curve has data further from the mean, so the red curve will have a larger standard deviation. And then question C is asking where's the median for each of these distribution curves, and we saw they both have the same center at 50, so you guys can label that as the median on your graph. And because these are symmetric curves, the mean is equal to the median. So we can go up here to 50 and label this as mean slash median, right there at 50. Let's see, and you guys can draw an arrow in there to show exactly where that is to yourself. Remember, our class notes or these examples are for you to refer to when you're working on the group problem and the lab assignment. So when you take the notes in the packet, you want to take good notes for yourself, or remember good places in the videos where you want to come back and ask more questions. Here in example 6 on page 63, we introduce what's known as the 68, 95, 99.7 rule. And what this rule tells us is that the standard deviation in the normal distribution curve sets the boundaries for 68% of the data, 95% of the data, 99% of the data. And you can see here on the graph, the 68% right here goes from -1 to +1. That's meaning -1 to +1 standard deviations. So we say approximately 68% of the observations fall within one standard deviation, and we use this sigma from the Greek letter, of the mean, and we use the Greek letter mu. So sigma, you can draw just like a circle with a line at the top. You can make a kind of messy S shape. It's the Greek letter for lowercase s, and we use it for standard deviation. Then if you look at the graph, you see 95% goes from -2 to +2. So that means that it falls within 2 standard deviations of the mean, 95% of the data. And then if you go all the way out to 3 standard deviations, -3 to +3, that's 99.7% of the observations. Now, depending on what the actual standard deviation is, that's going to change or squish the graph, right? Because you're going to have 2 times however much the standard deviation is. This case where you have whole numbers would only occur if your standard deviation was just 1, which is pretty rare. So let's look at an example here. So earlier we looked at the Iowa Test vocabulary scores for 7th grade students in Gary, Indiana. And it was close to a bell shape, so we went ahead and called it an approximately normal graph. So we can say that that distribution is approximately normal with mean mu equals 6.84 and standard deviation sigma equals 1.55. In your activity packet, you might notice these Greek letters with the numbers didn't fill in. So make sure that you write those in for yourself so you don't look back and wonder where these came from. And I think it was just a printing issue, so hopefully we don't have any more printing issues. So part A asks, what scores fall in the 68% of the data range? So 68% is 1 standard deviation. So the lower bound is going to be 6.84 minus just 1 standard deviation, so minus 1.55. And if we subtract, that gives us 5.29 is the lower bound for 68% of the scores. The upper bound is going to be the opposite. It's going to be 6.84 plus 1.55. And if we total that up, we get 8.39. So we can say 68% of the scores fall within 5.29 to 8.39. So that's the range where we get 68% of the scores. Now we want to do the same thing for the 95% data range. Now the 95% data range is 2 standard deviations. So we're going to say here 6.85 minus 2 times 1.55, because we have to take our standard deviation and multiply it by 2. And so that's going to be 6.84, subtract 3.10, and that's going to give us 3.74 as our lower bound. Our upper bound is going to be 6.84 plus 2 times 1.55. So that's going to be 6.84 plus 3.10. And we total that up, we're going to get 9.94. So we can say that 95% of the scores fall within 3.74 to 9.94. So it's our 95% range. So now they want to know what score is the cutoff for the top 5% of scores. Well, we may have to make an estimate here. So if we look back up here, we see, well, after 2 standard deviations, that's the top 2.5%. So that upper bound was 9.94. And then after 1 standard deviation, that's going to be 16% left over. So that's 8.39. So all we know is the top 5% of scores must fall between 8.39 and 9.94. So we can go ahead and estimate the cutoff for the top 5% is around a score of 9, but we don't know exactly where without more information. Now it's asking us what percent of scores are higher than 5.29. So if we look back at 5.29, that was our lower bound for 1 standard deviation. So we have to do a little bit of reasoning here. If we know that's the lower bound, we know that 68% fall in the middle, so we've got to figure out how much fall below. So if we say 100% minus 68%, that leaves us with 32% in the 2 tails. So that means half of that, or 32 divided by 2 equals 16%, fall below 5.29. Does that make sense? We have to take this 32% left over and split it among the 2 tails. That means down below 1 standard deviation is 16%, and above 1 standard deviation is 16%. So now we want to figure out, well, what percent are higher then? So we can say 100% subtract the 16% that are below, and we are left with 84% of scores are above 5.29. So in this situation, we had to use calculations, but then also some reasoning using the fact that we know the total area under the curve is 100% of the data. So we were able to use that information to help us solve this. Okay, let's go ahead and look at our next example on page 64, example 7. Remember, if you need more time to read through this, you can pause the video and copy down notes and then pick up with the next example. So now here we are at example 7, another application of this new 68, 95, 99.7% rule. So we talk about these normal distributions often, and we're going to use shorthand notation in this form with capital N, which stands for normal curve, just like function notation you might remember from Math 30. And then in parentheses, we're going to put the mean first, and so we use that letter mu, followed by the standard deviation. So in this example, it tells us summer monsoon brings 80% of India's rainfall and is essential for the country's agriculture. Records going back more than a century show that the amount of monsoon rainfall varies from year to year according to a distribution that is approximately normal, so close to the bell shape, with a mean of 852 millimeters and a standard deviation of 82 millimeters. So in shorthand, we can write N, and then in parentheses, we can say 852, knowing that's the mean, comma, 82, which is the standard deviation. So we want to ask here, between what values do the monsoon rains fall in 95% of all years? So remember, 95% is 2 standard deviations. So we can go ahead and figure out the lower, let's start with the lower bound. So the lower bound is going to be 852, subtract 2 times 82. So that's going to work out to be 852, subtract 164. And if we go ahead and subtract that, we're going to get 688. Let me double check to make sure I subtracted right. Yeah, so 688, and remember we're measuring in millimeters. Our upper bound is going to be 852 plus 2 times 82, or 852 plus 164. And so if we check that total, we get 1,016 millimeters. So 95% of all monsoon rains fall between 688 millimeters and 1,016 millimeters. So now, question B asks, how high are the monsoon rains in the top 0.15% of years? So if you look back at, oh, I went too far. If you look back at our chart on page 63, you can see the top 15%. Oh, well, they did 99%, but we would say using 99.7, the top 15% is 0.15% is 3 standard deviations. Let me type that out. That's a mouthful. So the top 0.15% is the upper limit for 3 standard deviations. Or sometimes we say 3 sigmas. You might have heard that phrase, 3 sigmas, used before. So we can go ahead and calculate that upper limit or upper bound. So we can say 852 plus 3 times 82, which is our standard deviation. So 3 times 82 is going to be 246. So it's going to be 852 plus 246. And my total came to 1,098 millimeters. So we can say in the top 0.15% of years, the monsoon rains must have been higher than 1,098 millimeters. Question C is asking the driest 2.5% of all years. So we can remember 2.5%, well, that's half of 5%, right? So the lower 2.5% is the cutoff for 2 standard deviations. Okay, so now we're going to calculate out our lower bound, which I believe we already did. So it's going to be 852 minus 2 times 82. And if we look back up in part A, we already went ahead and calculated the lower bound for 95%, which was 688 millimeters. So we can say in the driest 2.5% of all years, monsoon rains must have been less than 688 millimeters. Okay, so this finishes the examples for Module 2D. Go ahead and work on the group assignment, and remember that you can use the group assignment forum. You should use the group assignment forum to ask questions and talk with your classmates. And then you also can use the lab assignment forum if you have questions that you would like me to answer.